Welcome to a review session for the final exam in ECE 320A. This will be the last time that we meet prior to the final unless you attend office hours. And office hours, there's a couple more time slots before Tuesday's final. Hopefully you're aware that the final exam is on Tuesday from 10:30 to 12:30 p.m. The office hours are tomorrow from 9 to 11 and Monday from 2 to 4 p.m. If you have questions beyond today or over the weekend, if you can't make those office hours, send me an email and we can see if we can get the answers exchanged in an email fashion. Whoops. Wow. The process for the final exam shouldn't surprise you. 4 sheets of notes, a calculator, something to write with, and then everything else is a no. No cell phones, no computers, no textbook, no class notes, although you do get 4 sheets of notes that fit on an 8.5 by 11 piece of paper, and if you've been accumulating those, hopefully you don't have to do extra work. You can maybe just add to that. A lot of warnings. Questions before we get started? I guess I should remind you, I did just today put one more thing into the D2L material, and that's a list of topics that you should be capable of answering by Tuesday. It's only 5 pages long, but it basically covers the material in chapters 10 through 15 and chapter 18, which is the 2-port parameter material or 2-port circuit material. And the practice final exam has been there for a while, and that's still available to you to look at. I'm open for questions, or what I was thinking I could do is go over 3 problems that are somewhat more challenging, I guess, or more difficult from the student's perspective, and that would be a Bode plot, a convolution, and maybe a 3-phase power problem. Is there any particular order that you, pardon, 3-phase? You want to start with 3-phase? You're going to throw off my order. I had Bode plots first, but it doesn't really matter as long as I can kind of keep somewhat organized. Let's look at a 3-phase power problem, and you can pretty much expect it to be a balanced system. If you know how to do balanced problems, I'm going to assume that you can write KVL and KCL and do that for all 3 meshes, or however you try to analyze an unbalanced 3-phase system. The main thing is to understand how to work with 3-phase power. In this case, let's just sort of make it a word problem. Let's say that we have 3 different loads. Load 1, and now you just have to sort of remember what the terminology represents. Let's say load 1 is 24 kilowatts at a 0.6 lagging power factor. So you need 2 things to describe the power factor, the number and whether it's leading or lagging. And that's given here, which load 1 is what kind of a load? Lagging means it's more inductive than capacitive, so it's an inductive type load. Let's say load 2 is given as 10 kilowatts at a unity power factor. And what kind of load is load 2? That's purely resistive. And load 3 is then 12 kVA at a 0.8 leading power factor. And that's now a capacitive load. So we have 3 different loads, really with 3 different types of behavior, and we have those combined. We don't necessarily know anything more than that. We haven't been told one is a Y, one is a delta, they're all 3 Ys. We're just told we have 3 loads between our 3 lines, A, B, and C. And now we're told that the line voltage at the loads is, let's say, 208 volts RMS, and just so where we know where we're located, we're in the United States or in North America, we're at 60 hertz, if that matters. It might if we were given R, L, and C values, but we're not. The question now that we've been given the data is to now try to find the line current and the power factor of the combined loads, or the combined power factor of the loads. And the reason why I gave this problem in the form that I did is it gives us a good exercise in converting. We're playing with complex powers. We have a real power, we have a reactive power, we have apparent power, we have power factors, and you need to understand what those mean and how to relate all of those. And an easy way to do that is to think in terms of triangles. That's how I like to do it. And if we now have these 3 loads that are given, we can think of S1 in what way? What were we told about S1? Do you remember? S1 was 24 kilowatts at 0.6 lagging power factor. If we're sketching a triangle, what pieces of that triangle have we been given for the first load? The real part, which typically we draw horizontally. So this is now, we're given that we have 24,000 in the horizontal direction, and we're also told the power factor. The power factor is, depending on how you like to think of it, it's the cosine of the angle, where this angle then is that way, and I've drawn it up because it was positive, or it was a lagging, so it was an inductive load. Or you could, and we were told that this was 0.6. So this is now, if you wanted to think of it in that sense, you basically have a 3, 4, 5 triangle. The cosine of that angle, theta 1, is 0.6, or 3/5, and that's then the adjacent over the hypotenuse, and that gives you a 3, 5, and so you know the other side is a 4 if you forgot your calculator. But if you have your calculator, you can pretty easily find theta 1 if you wanted to. If that's the easier way for you to think of it, you can now inverse cosine that 0.6, and you end up with what angle? Isn't this like the 53 degree or something? Pardon? Anyway, if we had our protractor and ruler, we could draw it with a 3, 4, 5, and we would visually, or we would get the physical angle that we need. Did somebody calculate it? 53. So this is now 53 degrees that's been calculated. And if we want, we could now find Q sub 1, and that's going to be 4/5 of the hypotenuse. We could find the hypotenuse. This power factor is many different ways of writing it. We could say that's P1 over the magnitude of S1 if we wanted to. And again, that is this 0.6 value. And so now we could solve for the apparent power. The magnitude of S1 is now P1 times 5/3 is another way of thinking of finding S1. And then we can get Q1, which is just S1 sine of that angle theta. But if we have a 3, 4, 5 triangle, and we already knew what the adjacent side was, we know the opposite side is 4 to 5 in terms of opposite to hypotenuse. If you do the calculations, you now get 32K, and so in a directional sense, we're up here at J 32K, orthogonal to the real power. So our reactive power is 32,000, and that makes sense. It's bigger than our real power because we had a angle theta that was bigger than 45 degrees. And the cosine of that angle gives us the real part. Question? 24K is the magnitude of that horizontal line. I'm drawing it with an arrow to let you know that our lines now, we're dealing with vectors in a sense. It's going directly horizontal. The reactive power is going exactly vertical, either up or down. And then the complex power, which is both a magnitude and an angle, S sub 1, is going to be a vector quantity. It is going to have a magnitude and an angle. In this case, it has, did I even calculate the magnitude? Maybe I never did, but it's 40,000 in this case. So this particular length, if we divided or did the multiplication out, we have P1 was given us 24. We divide that by 3. That's 8,000 and multiply by 5. So that gives us our 40,000 for S1 if we wanted to keep track of all of this. That's the very beginning of this problem. That's load 1. And we have 2 more to go. But the second one is pretty easy. S sub 2, we were given that was 10 kilowatts. And so in terms of its 2 pieces, it's purely real, that complex power. It was 10,000 watts, or in terms of the complex power, S sub 2, that's 10,000. And S sub 3, what were we given on it? S sub 3, it said 12 kVA at 0.8 leading. So now the units tell us what piece of the triangle we have. S is what we have. We have the apparent power. We have the length of S, and with the power factor, we also have the angle. And it was leading, so now this one's going down. In terms of S3, we were given this line, which my lines aren't consistent relative to each other, but that's now 12,000 kVA, or 12,000 VA, or 12 kVA. And again, conveniently, we were told that was at a leading power factor of 0.8. So again, we have this 3, 4, 5 triangle. It's just our pieces are in different relationships. And maybe I drew that completely wrong. because 3 is not as long as 4. I can correct mine. You're probably writing in ink and being very frustrated with me right now. But let's say this is now 3 and that's now 4 and that's supposed to be 5. A little cleaner maybe. And this is now our angle theta sub 3, so that if we wanted to, you could say, oh, the cosine of theta sub 3 is the power factor of 3, or that's 3/5, or we know that that's also equal to p sub 3 over the apparent power. We know the apparent power, that was given. Thank you. Just making sure you're awake, because I'm not, obviously. I'm not even here. Did you not pick up on that? Hopefully I'll be somewhat coherent. There's S3 times 4/5, so we have something a little bit more difficult to divide. We have 5 divided into 12, but anyway, if you do that, you end up with 9600 for P sub 3, and Q sub 3 there's my 3/5. That ends up being 7200, but it's now going down in this direction, and our real power is always going horizontal. Which, all of that being said, we can add all of those complex pieces or powers together, keeping the real parts and the imaginary parts separate, and we obtain a total complex power of those 3 loads of 43,600, and we had 32 minus 70. Whoa, what just happened to 72? It went on a diet. Now it'll probably really be weird. This is now 24,800. Yeah, I think the note, my tablet's playing tricks on me. So it should be S total is the sum of those 3 loads, S1, S2, and S3. And that now gives us this total power of 43,600 plus J 24,800. Now what do we do? What were we supposed to be doing? Again, that might get you a point out of the 20 points that it was worth. So you've got 5%. Ow. So we want, what were we, I'm trying to find the blue line. Find the line current. How do we do that? Do you see the picture that's happening or that's taking place? We have these 3 loads, which we don't even know how they're connected. And they're actually 3 phases. And we're trying to find this magnitude of the line current. This is I sub L. And we were given this voltage, not the line to neutral voltage, but the line voltage or the line to line voltage. And that was 208 volts RMS. Is that clear? Now we can start thinking about some of our other formulas. If we were in a single phase problem, we know that the complex power is V as a phasor and the complex conjugate of the current. That's in the single phase. But we also have some very convenient three-phase complex power or total power and total reactive power formulas. For the total power, we have this square root of 3, V line, I line, and those are the magnitudes of those values. The magnitude of V line, the magnitude of I line, times the cosine of theta of the load. And in this case, since it's all three, we would have to find the angle of those three loads, but we basically have that with this total complex power. If we needed to, we could say, oh, the total three-phase power or reactive power is very similar. And if you added those up, that's what gives you your total complex power if you add those up orthogonally, so that you now have this square root of 3 V line, I line, and I'm going to just factor that common set of terms out. Or you now have this square root of 3 V line, I line, and this is now e to the j theta. That's just Euler, isn't it? So that this is now this square root of 3 V line, I line at an angle of theta. Another way of thinking of the total complex power. Now I'm just abbreviating e to the j theta as this phasor angle theta. Pardon? This is the angle of the total load. Or if you think in terms of this formula, you could say, well, that's S total at some angle of S sub t. And that now allows you to say, oh, the apparent power of the entire system is going to be the square root of 3 V line, I line, where those are the magnitudes. And we know V line as a magnitude. We can calculate the absolute value of the total power, and square root of 3 we can compute, so I sub L we can find. We could find it from that formula. We could actually find it from this P sub t, or Q sub t, if we find theta. So the drawing that we now have overall is this bigger triangle. Here is now our S total. This line was the 43,600 watts. This was our J 24,800 VARs. And this is now that angle that we have been referring to most recently, which is our theta total. And now that we have those two sides of that right triangle, we can use our geometry to calculate the angle theta, the hypotenuse, which is the apparent power, and use that to try to determine the answers to the questions that were asked. In particular, our power factor total is the cosine of theta sub t, or that's just this 43,000 over the apparent power, S sub t. And if you calculated that apparent power, which I guess I have in the past, this is now 43,600 over 50,160. So this is now the real power total over the apparent power. And what were we asked? Were we asked for the power factor? So the power factor we've now determined, if we compute that number numerically, does that end up being 0.869? What other piece do I need on top of the numerical value for the power factor? I need leading or lagging, don't I? And my drawing, I drew it up. Was that the correct direction? Since it was a positive, it's inductive. It's a lagging overall system. With those three loads combined, it comes out to be a lagging system seen at the terminals of those three loads. And our last piece to that, if we did, since I've already shown what the apparent power is, we now have this to be this 50,160, and we end up with this being 139.2 amps RMS. And now if somebody wanted to even extend that problem even further, they could maybe say, oh, you know what? You had a transmission line between those three loads. You could now sort of think of a single phase equivalent, and maybe somebody gave you this as 0.05 and this is J.02. We've just computed the line current magnitude. Whoops, it was 139, wasn't it? And now we could compute the voltage dropped across, or the power lost. In order to compute the voltage drop, we would need the angle of that current. Everything now is a vector. And we would have to make an assumption. If we assumed that this voltage was our reference voltage, then we would have to find the angle of that current. And right now in this single phase equivalent, I would have to convert that line voltage to a phase voltage. And that would be this voltage here, let's say from capital A to capital N. Here is little a. And maybe now somebody says, oh, what's the voltage seen, the phase voltage in the A phase, and assume your A phase is the reference phase at the load. Do you see how all of this could be worded to try to find? So if I wanted the complex power of the line, the transmission line, and I would need to say that, but I think it's somewhat clear if somebody said that the line, the complex power of the line, that's now going to be this impedance of the line. Times the magnitude of the line current squared, where this is now that 0.05 plus J 0.02, and that was the 139 something squared. Is that okay? So you could really go crazy with the different questions that could be asked about this. I could ask for the line voltage at the terminals of the source. And now you would be looking for something like V sub AB, not V sub AN. And you might have to then be told, is this a positive phase sequence or a negative phase sequence? And you might say, what is this if everything was in an ABC sequence? with the A, B, C sequence, then we were told the magnitude of V sub A, B before. That was our 208. We could now say that the V sub AN, whoops, that's the phase voltage magnitude at the load terminals. Do you know what that is? This is a balanced system. And now you need, on your crib sheet, hopefully you have something like, oh, V sub AB is equal to square root of 3 V sub AN, or maybe it's just V sub phi, at an angle of, wasn't it 30 degrees? And you could rederive that if you needed to. And that's how you could then find V sub AB or V sub AN in terms of that relationship. In this case, we have 208 divided by the square root of 3. That should give you your V sub AN. And that would be, whoops, yeah, that would be this guy right here. And if you assume that was your reference phasor, you might just assign that to have an angle of 0, and then you would need to back out your phase. Yes? So now once you have the magnitude of I, how would you find its phase or its angle? Now just go back to Ohm's law, maybe, and just say, oh, I know that V sub AN is equal to Z sub A, let's say, in the Y-connected version, I sub AA. Is that right? So now, if you know the angle of your impedance, which is consistent with the angle of your complex power, then you should be able to find your angle of I sub AA. Okay? Or depending on how you see it, you could say, oh, S is equal to V sub phi as a phasor, I sub phi star as a phasor. V sub AN, which V sub AN is your line to neutral voltage. And what we were given a line voltage, which was the line to line voltage, which is bigger than the line to neutral. The line to neutral is going from the line into there. Yes. I just assumed that. The question was, were we told it was a positive phase sequence? No, nowhere in here did I say that because we didn't need it to answer the first few questions. It was just when we were starting to answer or address potentially new questions that might say, what's the line voltage at the sending inside or the sending terminals, or what's a line voltage in terms of magnitude and angle. Then you're going to have to, if you're doing some conversions between line voltage and phase voltage, you need to know what phase sequence you're dealing with. But before we weren't asked that. So we didn't need that information. Just like we didn't need to know how our 3 loads were connected. Guess I should see my audience, huh? I've just been lecturing in the dark. Could have turned off the lights. It looks like that, right? As many mistakes as I'm making. Are we okay with power? You will be okay by Tuesday. So you have chapter 10 and chapter 11 in power. So single phase and three phase you need to be comfortable with. What do you want next, convolution or Bode? Bode? All right, so where did Bode go? Suppose we have the following transfer function, h of s as 25s over, whoa, where did it go? Who knows? (25s) over s plus 0.5 and s squared plus 4s plus 100. And you're asked now to sketch the Bode plot of that transfer function. Pardon? Now you should start seeing these pieces, the different terms, the different factors that you're going to have to sketch. You have a gain piece or a constant piece. You have a zero at the origin, and you have three poles. You don't yet know what kind of poles you have, but in this class we've agreed even if they are complex, we get to approximate those as two real and equal poles. So as long as you can sketch real factors, you're okay. You just have to be able to know how to convert a complex or approximate, for this class, complex factors from real factors. Are all of your poles in the left half plane? You can see that by inspection, correct? They've been factored into single, linear, or quadratic factors, and the quadratic factor needs to just have both coefficients present and positive, and they do. And the linear factor is fine. You know that that one's going to be in the negative because if you solve that for s, it would be s equal to minus 0.5. So you do have a stable system, and that's really the only systems we've learned to sketch in terms of Bode plots. That being said, is this, so now I think the first thing that I would probably do is I would factor that, or I would find the roots of that polynomial, just to see, do I have two real unequal roots, or is this a complex set of roots that I need to approximate? And if we looked at completing the square, to get that s squared plus 4s, I could square something like s plus 2 to give me the s squared plus 4s plus 4, and 4 plus something else, which is 96, will give me back that 100. So this now is looking like a quadratic, I'm sorry, a set of complex poles. Because now we have this 96, we could write that as, it's almost 10, but something like that. So we now have the square root of 96 in the vertical direction, almost 10, and in the horizontal direction, a minus 2. So we're at minus 2 plus and minus j10 for those two. They're pretty close to the imaginary axis, and we've agreed to go ahead and swing them all the way down to become real to sketch them. In reality, they wouldn't be that way, but we're okay. I'm okay with you sketching them that way. Meaning, if we now have this complex factor, now I'm maybe going too far afield, but we have s squared plus 4s plus 100. We've just seen that it's complex, so this constant piece actually represents the natural frequency squared. That's the distance away from the origin. And that's what we've agreed to use when we rotate it around. So the square root of 100 is how far away we are from the origin, and that's going to be our two real equal poles. This now says that omega sub n squared, being 100, gives us a natural frequency of 10. That's how far away we are from the origin. If we were looking at this in the complex S-plane, our poles are basically right there, and they are a distance away from the origin of omega sub n, but we've agreed to go ahead and allow those to be moved down and become real, and now this is a distance of 10. It's in the left-hand plane. I'm just emphasizing that by minus 10, which really says that we are going to agree in this class that we are going to replace that s squared plus 4s plus 100 by an s plus 10 squared, which really gives us s squared plus 20s plus 100. So there you can see the damage or the severity of our approximation. We're approximating 4 with 20. But that's okay. But there is where the error is in our sketch, or that's where it arises. But don't worry so much about that. I want you to just be able to do that approximation. And now we are ready to sketch this new h of s, which started out being 25 over s. And this was s plus 0.5, and now we're going to say, oh, that's just two real poles at s plus, or two factors at s equal minus 10. Is that okay? And now we need to do what to that transfer function? Now we have to get it into the time constant form. It's in the pole zero form. The time constant form says that we need to normalize those constants 0.5 and 10 to be 1. And if that squaring is confusing you, I would just write it out. I would say, okay, we have 25s, and then we have 0.5 for the linear one. We have s over 0.5 plus 1, but now I have one of those, but I actually had two of those. So that now this becomes 25s over 0.5, s over 0.5 plus 1. That's now 100, s over 10 plus 1 squared. Is that okay? We simply need to clean up the constants. We have 25 over 100, or we have 1 over 4. And 4 times a half gives me 2. I have 1/2, so that now I have 0.5 s over 0.5 plus 1, s over 10 plus 1 squared. And that's now in a form that we can start to sketch. Are there questions on where that came from or how we find that? Now we have to identify all the pieces, and we have really a constant piece, a zero or pole at the origin, and we have some linear factors to deal with. If we look at the constant term, And I think it's helpful when you're first learning how to do this, and even now, is to just write out what you have, each factor, and then you can sketch it. The constant piece, in terms of its magnitude, is 20 times the log of 0.5, or that's 20 times the log of 1/2, or that's 20 times the log of 1 minus the log of 2. That's 0, and what have we learned what the log of 2 is? That's this 0.3. So that now we have this is minus 6 dB, and that's going to be contributed for all frequencies. That's what that upside down A means, for all. That constant then contributes for the magnitude minus 6 dB across all frequencies. And what's its phase? It's 0 degrees for all frequencies. So we could even score points by not doing anything with the phase. If it was if we had a negative sign, then we would say the phase is minus 180 degrees for all frequencies. Then we have this 0 at the origin. And what do we know is special about zeros and poles at the origin? Pardon? It's always sloping in terms of its magnitude. In terms of its phase, it's constant, isn't it? So if we looked at the magnitude of this one, we have this, it's always sloping, and what is its slope? It's plus, since it's a 0, 20 dB per decade, or equivalently 6 dB per factor of 2, octave. A decade is a factor of 10, an octave is a factor of 2, if you needed to look at a smaller interval of frequency. Now, that's fairly vague right now. Oh, I have a line that slopes at 20 dB per decade. You need to know where to fix it, pin it on your Bode plot, and you can do that by picking a convenient value of omega, which is 1, and with omega equal to 1, we have 20 log of 1, which is 0 dB. So this is sloping at plus 20 dB per decade, and it's passing, or passes, through 0 dB at 1 radian per second. And that's how we pin that one down to get a specific location. Its phase looks like what? Do we do Goldilocks? Yes, question? So the question was, is it always going to be 1 radian per second? We now have where it passes through 0 dB. We have this S sitting upstairs. And if we're looking at the frequency response, which says, oh, we're going to be sketching j omega, and we're sketching it in terms of dB, and dB is 20 times the log base 10 of the magnitude of whatever it is that we're sketching. So that now this is, what's the magnitude of j? How far is j from the origin? That's the unit j, isn't it? It has a coefficient. It's hidden, but it's 1. It's 1j. So we're rotating up on the vertical axis. We can forget j. No offense to anybody in here that's named j. Sorry. We're not forgetting you. We're forgetting the complex, or the square root of minus 1. It's magnitude. But now we have 20 log of omega. And that's always going to be 0 dB when omega is equal to 1. So does that help answer? So this now is that's why it's sloping at 20 dB per decade, because we're sketching our independent variable on our Bode plot is log of omega. If you think of this as a straight line, y is equal to mx plus b. We do not have a we don't have a plus b, we just have the x. We have y is equal to mx, and m is the 20, log of omega is our x. That's where we're getting our 20 dB per decade. So this is the way that we can justify that passing through 0 dB at omega equal to 1. Now, what was our phase? If we go back to this picture, we have a 0 sitting right here. And now we are marching along j omega, or underneath the circus tent. We're just walking up there. And if I'm measuring the angle relative to that horizontal, no matter what the omega is, that angle I'm always turning is 90 degrees, isn't it? So that 0 is contributing 90 degrees for all frequencies. And our phase now for that 0 at the origin is 90 degrees for all omega. This was the S-plane. I know you're seeing the circuit's tent, but that's fine too. Now we have two more factors to describe. We have a pole at s equal minus a half, which is less than 1, so it's going to break before omega equal 1. It's going to break before we get to that crossing of the 0 at the origin. That's okay. We now say this has a magnet, and now we need to play with, well, the phase, I guess, worries about Goldilocks maybe, but here the magnitude is 0 dB until we get to the break frequency. Which occurs at omega equal to 0.5 radians per second. After we hit the break, we then have a slope, and this was a pole, so now we're going down at minus 20 dB per decade after we break. So we really are doing two approximations, and we're connecting those right at the break frequency for our magnitude. This now looks like that. This slope is minus 20 dB per decade. This point is omega equals 0.5, and this is right along the 0 dB line. That's that factor's sketch. What about the phase? Here's where we have our three different values. We have our low value, it's 0 degrees a decade before. So now just remember the phase transitions over a 2-decade interval, and that 2-decade interval is centered on the break frequency. So it's 0 degrees a decade below the break. It's right at minus 45 degrees. It's a pole right at the break at 0.5, and we're assuming that it's at its ultimate value of minus 90 degrees a decade above the break, or at 5. And these are all radians per second. And finally, we can which we've approximated by s plus 10 squared, which in time constant form looks like s over 10 plus 1, quantity squared. In this case, the magnitude is again 0 dB, until we reach the break, which is at 10 radians per second, or its natural frequency. After that point, then, it slopes at what? Pardon? Now it's negative 40 because we've approximated that quadratic by 2 linear, and so we have 2 poles now on top of each other. It's now going down at 40 dB per decade after that break at 10. The phase, even though it's a double factor or a quadratic, it's still only spreading its change over 2 decades. Again, centered at the break, but now it's going to have much more change in phase. It's going to have twice the phase as a single factor. It's 0 degrees a decade before the break, which in this case is then 1. It's minus 90 degrees right at the break of 10. And it's now 2 90s, negative because it's poles, a decade beyond the break. Questions on those word descriptions? Yes. So now the phase, if we sketch this phase, here's our break. We center it again around the break, but now it's going to be 0 degrees. Then it goes all the way down to minus 180, but it's still linear between those two. So it looks the same. I'm not sure if that's answering your question. I thought the question was, what's the phase look like for a quadratic factor? Oh, what if we had a cubic at the same? So what if we had the following? What if we had s over, let's say, 20 plus 1 cubed? And let's say that was a 0. Maybe I shouldn't. Call that j omega. What's this look like? And this is now the phase of that factor. If I said, what's the phase contribution at high frequencies for this factor, j omega over 20 plus 1 cubed, what would you tell me it is? What did you say? Each factor gives you how much, so now we're talking phase. Each factor gives us how much phase. If I were to go back up to this pole, I'm sorry, this 0, that 0, how much phase can it ultimately give me? It's only going to give me 90 degrees, isn't it? Each one. So each one, and how many do I have here? I have 90, 180, 270. So I'm going to be contributing 270 degrees at high frequencies. Which, what's high frequency in this particular case? Something bigger than a decade beyond 20, 200 or above, we would consider high. So at 300 radians per second, this factor will be contributing 270 degrees. If we sketched that, we would be here at 20. That's our break. 2, and then this is 200. And now we're not at 90, we're not at 180, we're actually all the way up at 270 degrees. And before we get to a decade before our break, we're at 0 degrees. A decade after, we are all the way up at 270. And right here, if I had drawn this very effectively, that would be at plus 135 degrees. But the shape looks the same, it's just the slope, it's more pronounced each factor we introduce. Is that clear? Where was I? Oh, trying to sketch the ultimate magnitude and phase for our transfer function. What would my axis look like? Ooh, yours will look better than that. And when I'm asking about what this looks like, I'm basically saying what frequency should I be putting on here? And now you need to go back and look at some of your pieces, and you would say, okay, where's sort of my highest frequency? Looks like 100 right now. That's my highest. What's my lowest I need to worry about? That's that 0.05. So now if I go to 0.01 up to 100 or beyond, so now I need to be going, let's say from 10 to the minus 2, that's the 0.01, 10 or 0.1, 1, 10, 100. So let's say that's good. And my constant factor gave me minus 6 dB, didn't it? That was my constant factor. I'm sketching the magnitude of my transfer function. That was due to the constant. I also had a, I probably made 6 dB way too big. I did. Oh well. There's 20 dB. And there's 40 dB. The reason I'm doing that is, let's say there's minus 20 dB. This is now my 0 at the origin. Now what else do I need? I wished I hadn't drawn that minus 6 so poorly. That's more like minus, I can erase it, I guess, but now I have to erase every one of those dashes. Is that okay? What else do I need to sketch? So this was the, well, I already labeled it, didn't I? I have 2 more things to add to this. I had the pole at 0.5, so that's going to be where? If you look at 0.5, that's about 0.7, 70% of the distance between 0.1 and 1. So if I say that's 0.5, I'm now going down at 20 dB. And finally at, was my quadratic right there, and I need to go down, what did I do that for? Sorry. My pole was at 0.5, wasn't it? My phase starts a decade before that. But here I need to go to 5, 70% of the way, and drop down to 20. And then go up to 50 and drop down another 20 so that that would be my magnitude sketch for the 0.5 pole. Then I have another pole at 10 that's supposed to be sloping twice as fast as that other one. Now I have to put all those pieces together, which means what I would do is I would go to the left or lower in frequencies, bless you, until I get to the left of anything that breaks. And then I would say, okay, right here, what do I have? I have -6 and a -20. That's actually going to give me a net of -26. My total curve is going to, let's say, go through that point, and it's going to be sloping up because that's where I'm coming from with my 0 at the origin. If I do that, I'm down here 6 dB below 20, -20, and I come up here until I reach the first break, which is at 0.5. I was coming up at +20. Now I'm coming up at 20 and down at 20. I'm now going to go flat until what? Until I hit 10, and then I'm going to go parallel to that. This is going up at +20 dB per decade. This is going down at -40 dB per decade. Is that okay? And then I need to do my phase, which let me quickly do that. The phase curve, I still have my frequencies. Ooh, that was 10 to the -2. Where do I start my phase? At +90. And I'm continuing to go level until I reach, here is, let's say, 0.5, but I need to be a decade before that and a decade after that for 0.05 and 5. Meaning this pole is going to be giving that kind of a shape. And my other pole, 2 poles, were centered at 10. So I go back a decade, I go up a decade, and now that one is going to be transitioning from 0 all the way to -180 over a 2-decade interval. And now I have to add all of those pieces together. Meaning, I'm flat at 90 degrees until I start changing slope at 0.05. At 0.05, I'm going to go down parallel to this 0.05, or 45 degrees per decade. So at 0.5, I'm going to be right here at 45. And if I didn't have that additional pole kicking in, I would have been at 0 when I got to 5. But I have to quit that and change my slope once I get to 1. And now I'm going down really fast, aren't I? Because I have minus 45 and minus 90. So now I'm going down at minus 135 per decade. So if you went down 135 degrees from this point over at 10, then you would be at some location. And well, you would say this, and now you would be down here, and I would start to connect that until I reach the 5, and when I reach 5, I'm actually going to only have this pole acting, and it's going to get me where? Right on top of it, because this minus 90 is canceled by this plus 90, so eventually I'm only going to have a net angle of minus 180 at high frequencies. I have a 0 and 3 poles, so I cancel one of the each, and I end up with 2 poles net. So at high frequencies, I'm going to be at minus 180. And if I do what I just tried to describe, I'll look something like that for my curve. Are there questions on Bode plots? Wow. You guys are experts at Bode plots, and you know that you can quickly sketch these in MATLAB, right? But now you have a way of checking your work, or if you want, you could sketch it on a napkin and then say, oh, okay, my Bode plot from MATLAB is consistent with what I thought it should look like. You can check its high frequency phase, you can check the slope at high frequency, you can check the slope at low frequencies just from these sketches. Question? So between 1 and 5, what is the slope of that phase curve? Isn't it obvious from the sketch? At this, in between 1 and 5, what slopes are active? That's how you can check. You have this green one coming to us from the pole at 0.5. So that's giving us minus 45 degrees per decade. This black one is associated with the pole, the 2 poles at 10 that we're approximating our quadratic with, and that gives us minus 90. So we have minus 90 plus minus 45. This is supposed to be minus 135 per decade. It's additive. If we had a 0, then we would make the change algebraically, meaning if we were going down at minus 90 and plus 45, we would be at a net minus 45. Does that make sense? So you need to algebraically add up all these angles. And yes, to be accurate, I should be labeling this. This is now minus 45 degrees per decade. This is now minus 135 degrees per decade. And this is minus 90 degrees per decade, ending up at a value of minus 180 degrees at high frequencies. Yes? I'm not quite sure I'm following what you're asking. If there wasn't a 0 at the origin, if there was no 0 at the origin, we would start at 0 degrees for our phase. And then we would come right along this dashed line until we hit the phase contribution of our pole at 10, which starts at 1. And then we would be going down again. We would be sloping at minus 135 degrees per decade, because this 0 at the origin is not giving us a slope, it's just giving us an angle. It would be minus 135 until we got a decade beyond the first pull factor, and then it would be minus 90. So the slopes would be the same. The net location would be different. All right, convolution. Let's see what we can do there. Suppose I give you an x of t that starts at with a value of minus 3 at time t0 and goes to 5, and it reaches a value of 2, and let's say that h of t begins at 2 and ends at 5, and it's constant and has a value of 4. Knowing what you know about how I grade now, what's missing on this figure that you would have to supply? I might not supply it to you, but if you're computing the convolution of these two waveforms, what's not explicitly shown? I thought I fell asleep. The equation of the line segment. We need, or you need to give me what that is. So you know this intercept is minus 3, and it's actually, if you look, that's now 3, so it's going through 3. It's sloping at a slope of 1, so this is now x of t is equal to t minus 3. That one's pretty easy to parameterize. Now, which of these, well, before we even do anything, can you tell me over what intervals of time t will y of t, which y is I'm assuming I'm calling that the output of the convolution of h with x, over what time interval is this going to be non-zero? Does everybody see that? If h of t represents an impulse response, that basically says I hit it at 0 and it doesn't start shaking until 2 units of time after. And my input is actually starting at 0. So it starts at 0, but the impulse says, oh, I can't do anything until I'm told by my behavior, and that behavior is I need to start shaking 2 units of time after I'm hit. So that's where the 2 comes from. The 5, I continue to shake it until 5, but this guy, 1, doesn't start shaking from 5 until 2 after that, so that's 7, and then he keeps going until 5 units after you finally stopped shaking. And you stop shaking at 5, and he continues to move 5 units thereafter, so that's giving you the 10. Or add 0 and 2, and add 5 and 5 if these are all not stopping and starting in terms of their functional values. Questions on that? So that could be a quick question that might be asked. Which of these would you flip and slide? The h, right? The h is a lot easier. So if we now look at h of minus lambda, what color did I have it? We just rotate it around that vertical axis, lambda equals 0. Pardon? Thank you. And now if we want h of t minus lambda, because t we are adjusting, and we could make t really, really negative if we wanted to, and that would put it over here at t minus 2 and t minus 5. And now what we want to do is adjust t. That's how we're sliding that h of t minus lambda from small lambdas, negative infinity, all the way up to big lambdas, positive infinity. And we're looking for unique overlap pictures or patterns that happen as that signal, in this case the impulse response, slides through the input waveform. And if we simply remind ourselves of what we had for x, whoops, when do we not have any output? The output is going to be 0 as long as this t minus 2 stays to the left of lambda equals 0 in x of t. So we're going to have no overlap, or y of t is 0 as long as t minus 2 stays below 0, or as long as t is less than 2. And that is consistent with that very first line that we wrote when y of t is non-zero. Let's look at some overlaps. And I apologize if I'm doing this pretty poorly in terms of sketching, but when is this picture going to be true? And again, this shape is now what? Luckily, we didn't flip and slide it, so the t just becomes a lambda, and we now have lambda minus 3 when we need to integrate. This picture, this overlap number 1, is going to occur when this rightmost edge of h of t minus lambda goes beyond lambda equals 0. So that says t minus 2 is greater than or equal to 0. And I did this on purpose. Do we have to get too nervous about what's happening here? Even though it looks like something different is happening, we still have exactly the same functional description. So we don't have to worry if we come across that point, which is 3. We really just have to worry about this edge, which is lambda equals 0, and this edge, lambda equal 5, relative to t minus 2 and t minus 5. Is that okay? And this width, or inner region of support, is 3, which is less than 5, so this black piece is going to be totally on top of x at some point. So we're going to have an initial overlap, a total overlap, and then a partial overlap, and then nothing. Is that clear where we're headed? Okay, so this happens for t minus 2 greater than 0 and t minus 2 less than 5. Maybe we can't see yet what might be happening, and t minus 5 less than 0. And we need to take the pieces of those that happen first. So we just said t minus 2 needs to be less than 5, and t minus 5 less than 0. This one now says t is greater than or equal to 2. This one says t is less than 7, and this one says t is less than 5. Well, that one we don't need to worry about because it's not going to happen yet. So let's not, that crossing is not going to occur before the other crossing is going to happen. And so this is going to occur when t is between 2 and 5. And what's wow, why is that? What's my y of t expression? Some integral, and it's going to be 4 times lambda minus 3 d lambda. But what are my limits of integration? Now I'm looking at where the blue and the black are both crossed. And that's between 0 and t minus 2. And that's not the same as those two limits, but that's the limit on time when this particular result is valid. So if you compute this integral, that integral result will be true between those values of time t. And these limits of integration are not necessarily the same as your interval when it's valid. Is that clear? All right. What else do we have? Now we have the total overlap, don't we? This overlap picture occurs when t minus 5 now is bigger than 0 and t minus 2 is less than 5. Or this is going to be when t is bigger than 5 and less than 7. And my expression for y of t, the integrand is the same. It's still 4 and lambda minus 3 d lambda. What are my limits of integration? T minus 5 to t minus 2. Then we have the next partial overlap. Maybe that's poorly drawn. That shouldn't, well, it doesn't matter, I guess. When does this pattern occur? We needed t minus 2 to get bigger than 5, didn't we? And we need t minus 5 to remain less than 5. Is everybody following this? Or this says now t lives between 7 and 10. And what do we have for our functional form of that y of t? We have exactly the same integrand again. So once you've integrated that, you can just keep copying that result. You just have to evaluate it at different locations. This is now t minus 5 to 5. And the no overlap is when t minus 5 gets bigger than 5. And I'm not even going to sketch it. I'll let you pull out a napkin and sketch it. Questions? Are we good? Or we're done? Those may not be the same, but I want you to be comfortable and confident going into the final. Reminder, office hours tomorrow morning from 9 to 11 or Monday from 2 to 4. Come see me, or if you can't make that, send me emails and we can try to answer your questions that way. Good luck on your finals. Enjoy the rest of reading day. And there was a homework packet, homework number 9,